What you're seeing here is the refraction of light in water. If this feels remotely weird for you, don't worry, this is what we're building up today. In this video, I have included various tricks and surprises like this. Phenomena that you've seen and heard of will appear in a brand new and utterly satisfying way. In the last video, we were talking about light. We demonstrated a very weird experiment which could be explained using a set of rules involving rotating arrows. In case you've forgotten, let me summarize them here. The grand principle of our theory is that the probability of an event is the square of a so-called final arrow. If its length is 0.2, the probability is 4%. But how do we calculate the final arrow? To each way that an event could happen, we draw an arrow, then add them up together to give the final arrow, the square of which is the probability. With these rules, I guarantee that we can explain each and every phenomena of light with empowering accuracy, so I'll only show you the simplest examples. Okay, so that's the recap. Today, we start our journey with light reflecting off a mirror. We have a source S that emits only yellow light at the mirror. At P, we have a photomultiplier that detects photons. We want to calculate the chance that P would make a click after a photon is emitted from the source. To prevent photons from directly going from S to P, let's put a wall to prevent that. Now, we'd expect all light to reflect off the center of the mirror, since it's where the angle of incidence equals the angle of reflection. Also, it's fairly obvious that the two ends don't have anything to do with the reflection, right? So we might think in this way. Let's look what quantum theory has to say. The probability is found by adding arrows for each way one event could happen, then square the final arrow. In the experiment of partial reflection, there were two ways one photon could end up at the detector. In this case, there are millions of ways a photon could end up at a detector, so we should add millions of arrows. The best part of this is that the animation looks gorgeous. But the bad thing is, adding millions of arrows is tedious. That's the worst thing ever. Worse than coronavirus. And now you might think I'm crazy because hey, for most of the paths here, the angles aren't equal. But I'm not crazy because that's the way how light really goes. How can that be? For now, let us discretize the mirror into a definite number of little squares and consider only one path for each square. As the squares get smaller, our calculations get more accurate, but also harder to do. Now, let's draw a little arrow for each way light could go in this situation. Let us consider the length first. You might think that the arrows at the center of the mirror are by far the longest, and the arrows at the ends must be very short, because the center has more to do with the reflection. No, we should not make such an arbitrary rule. The right rule, what actually happens, is much simpler. The photon that reaches the detector has an equal chance of going all paths, so all the little arrows have the same length. Now we go on to consider the direction, and here's where the fun begins. As you remember from the previous video, the direction of a particular arrow is determined by the final position of an imaginary stopwatch that times a photon as it goes. Therefore, the direction of each arrow corresponds to the amount of time related to the path. Here, I coded it so for each path a photon could go, the arrows turn at a constant rate of 1 cycle per second, and I want you to guess what will happen. Well, let's run the simulation and check out. Did you see that clearly? I'll replay the animation, and this time I want you to pay attention to the arrows that rotate at the bottom. Clearly, the middle path uses the least time, so the stop of the arrow spreads from the middle to the two ends. Can we extract any physics from here? To proceed, we add these arrows and see what happens. At first, the arrows from the far left curl together and don't go anywhere. Then at the middle, arrows point at nearly the same direction and really add up. Then at the far right, arrows again curl together and go nowhere. The final thing to do is to draw the final arrow. If you'd notice, that's a sizable arrow. Trumpets please! Our theory of quantum electrodynamics predicts that light does reflect off a mirror. There are several things to notice here. First, the arrows at the end of the mirror wander around and don't contribute much. It wouldn't affect the result much if we chopped off the ends of the mirror. You can say that since reflecting off the ends is an act of extreme stupidity, the photon is punished by arrows cancelling each other. On the other hand, it's the middle of the mirror that gives most contribution to the final arrow. This is because time is nearly the same from one path to the next when time is least. Going at the middle is a smart move, so the photon is rewarded by arrows adding together. As a treat, I'd like to bring you into the continuum limit. We slice our mirror into hundreds of squares and add an arrow for each path. As I said, this is really hard to compute. But since we're humans, when we have something hard to do, we throw the problem to the computer. It's really satisfying to watch. Ready? Go! When we add the arrows, it's even clearer how the far left surmounts two arrows circling into each other and how the middle part contributes to the most of the length. As we go to the far right, though it's off screen, the arrows again wander around and go to nowhere. Nice and neat, isn't it? To summarize, where time is the least is also where the time for nearby paths is nearly the same. So the little arrows add up to a sizable length, and that's where the probability of reflection is determined. Therefore, in classical physics, we can cheat a little bit and say that light reflects off only the middle of the mirror. For beginners, that still sounds awkward and nonsense. It doesn't seem like that real-life physics is all about wasting time calculating arrows whose sole purpose is to cancel out. To impress you that we're on the right track, I'm going to perform a nice trick here. We move the mirror to the far left and chop off some of it. Now, we still have a large piece of mirror, but placed at the wrong position. As before, we set up all possible paths and calculate the arrows. Based on the last experience, what result would you expect? Ready? Go! Adding the arrows together, we find that because of the large differences in time, these arrows go in nice circles and do a great job at doing nothing. On the right hand side, though the arrows still make certain contribution, it isn't much. It seems that we should stop wasting time fiddling around with them, don't you think? Here's the trick. I carefully strap away some of the mirror. Usually, removing the mirror makes less light be reflected. But if we add the arrows, look what happens. Now we actually get a substantial arrow. Compare that with the original one. Since the final arrow is nice and long, our theory now predicts the reflection to be strong. How can this be? Some of you clever viewers already know where I'm going. This is called a diffraction grating, and it works like a charm. Isn't it wonderful? If you take a piece of mirror that doesn't reflect, scrap some of it off, then suddenly it reflects. The grating I just made is tailor-made for yellow light. It won't work for purple light. As the stopwatch turns faster for purple, our grating directs purple light to another spot. When we shine white light onto the grating, red comes out in one place, orange in another, yellow another, then green, blue and purple. A colorful rainbow emerges. I can easily go on to talk about how lasers and holograms work, but there's too many good things to talk about, so I'll leave them out. The example of grating tells us that we cannot ignore parts of a mirror. We have to consider all possibilities, not just the ones we think are important. The next phenomenon is more familiar, the refraction of light in water. It is also the example you saw in the beginning of this video. This time, we put the photomultiplier under water and pray it is waterproof. Once again, we want to calculate the probability that photon ends up at a detector. To calculate this, we consider every possible path light could go, including the silly ones. It seems that light goes slower in water. I'll explain why in the next video, but for now, we'll take it as given. The slowness makes it more costly to travel underwater. Suppose you're on the land and your boyfriend or girlfriend is drowning in water. If you don't have one, I cannot help you with that. Anyways, let's suppose you want to save him/her. There are several candidates for the path of least time. You can run straight towards the him or her, but it's not the fastest path. You can also run on land and enter water only when necessary, but this path is also too long for being the least time path. The third candidate is this path. If you go this path, you love swimming more than your spouse. It's intuitively clear that the path of least time should reside somewhere between the first and the second path. Now, let's run the simulation and find out. Again, photons get punished when they go the stupid path, where arrows go in circles and cancel each other. Where the most contribution comes from is nearly the path of least time, which is also where the classical physics predicts it to be. Lo and behold, our theory predicts that light bends in water, just like you'd see when your iced lemonade comes with a straw. By the way, I made a huge simplifications in the above examples. Did you see it? I assumed light always goes in double straight lines that form an angle, but we don't have to assume that light goes in straight line. Our theory explains even that. So now we have here a source and a photomultiplier. In between is certain clever paths and certain stupid paths. For each stupid path, there's a nearby path that looks nearly the same, but takes less time to travel. Remember, we assign to each possible way an arrow, even if light goes in curves. We do our usual job and run the simulation. This time, the result might surprise you. For the paths around the normal one, the arrows add up as we'd expect. But for each stupid path, the arrows cancel each other since they're punished for going the crooked way. By induction, we immediately see all crooked paths get their amplitude cancelled, so the major contribution comes from the straight line paths. The physical interpretation here is that light goes in all weird paths, either clever or stupid. The final result comes out as if light only goes in straight lines. This is a good approximation. It's important to note that merely the arrow of the straight line isn't enough to account for the probability amplitude. The nearby paths also add value to the final arrow and make important contribution. Therefore, light doesn't really only travel in straight line. It kind of detects the nearby paths and uses more core of nearby space. There are certain rules in classical mechanics that say light goes in straight lines, light reflects off a particular angle. While being good approximations, as we squeeze light very tight, these rules fall apart. Below, I'm going to perform another trick. This time, I place a pair of blocks between S and P, so light must pass through the spacing to end up at P. For the sake of simplicity, let's assume that light goes in straight lines again. Now, we put another photomultiplier at Q, which requires tremendous amount of stupidity. We can straight up predict what would happen. At P, arrows add up to a sizable length, and at Q, arrows cancel out and go nowhere. And the results are indeed as such. So, the photomultiplier at P clicks a lot, and that at Q does not click. From here, we squeeze the light. Notice what happens. When the arrows from the edges disappear, it actually shortens the arrow at P and lengthens the arrow at Q. This means that Q will start clicking while P will click less often. Let's see what happens when we squeeze light to the limit. In this case, only one path could a photon take, so the little arrow is itself the final arrow. Recall that the probability is the final arrow squared, so the probability of going to Q and P are the same. Furthermore, if we put detectors at A, B, and C, then the probability of going to any one of these detectors are the same. You see, when we squeeze light too much, it gets mad and does not cooperate with us. I'd like to put this in another way. We are pretty sure that the photon has gone through the slit and the uncertainty in position is really tiny. However, the photon has an equal probability to go in any direction it wants, so we are not very sure about its momentum. For those of you who study quantum mechanics, here it is. This is the famous Heisenberg's uncertainty principle, except in this case, we don't have fuzzy statistics or numbers, just rotating arrows. This is not our first encounter with this theorem. Remember when we said light goes in straight lines? We are very unsure about its position. It goes 300,000 miles per second, very hard to detect. And hence, we can be really sure about its momentum, and we can safely say that it goes in straight lines. The following is the final trick of the day. It's kind of a surprise, so I won't let you know what it is yet. Now, we draw a straight line here, and never mind me, I want to let light go through this line and then end up at a detector. The results are as normal. I believe I don't have to stress the behavior anymore. Now, let's have some fun. We want to fool the light so all paths take up the same amount of time. How can we make the shortest line take as much time as the longest lines? Well, light goes slower in water than air. It turns out that also, light goes slower in glass. So, we put just the right thickness of glass, so the time for that path lengthens to become exactly the same time as the longest path. The adjacent paths are longer, and by definition, they already take more time than a straight line. Therefore, we put a layer of glass slightly less thick than the first one. The closer we get to the longest path, the thinner glass we need. Now, see what that is? We have a lens. All of the arrows point at the same direction, so our theory predicts that lens focuses light really strongly. We started with the ideas of arrows, with seemingly no mechanism, no reasoning, no causality, no nothing, and from there, we derived that light bounces off a mirror, light bends when it goes into water, and light focused by lens. It also explains things like the diffraction grating, the uncertainty principle, and so on to every phenomena of light. Over the past few minutes we have gone through a lot, and I ought to congratulate you for finishing the video. I hope you have learned something new from this. In the next video we will take a step backwards and actually tell you how physicists calculate arrows and probabilities. See you there!